Welcome to the Spring 2021 Knowledge Graphs seminar. This seminar is being co-organized by myself, Naren, and Mike. Our motivation in organizing this seminar has been that we are seeing knowledge graphs being used for lots of different applications, including web search, question answering, and data integration. And if you go to many leading conferences in NLP and vision, you see knowledge graphs as the choice representation for output of NLP and vision algorithms and for output of machine learning algorithms more generally. So our hope is to convey through this seminar the basic ideas, concepts, theories, and application about knowledge graphs. The importance of this topic has also been recognized by National Science Foundation. Last year, they funded about 20 different knowledge graph projects as part of their Convergence Accelerator program. We'll be hearing from Chaitanya Baru next week, who will tell us about some of the projects they are funding. Even though this is a seminar series, there is a structure to it. First few sessions are going to be focused on what is a knowledge graph? What are some of its data models? Then we will talk about how we create the knowledge graph, different techniques for knowledge acquisition for it. Once the knowledge graph has been created, how do we reason with it, and how it can be used with modern AI algorithms. Towards the end of the series, we will talk about applications and where are the current edges of research in knowledge graphs. The course design this year is a little bit different. Instead of doing one 2-hour session each week, we are doing two 80-minute sessions on Tuesday and Thursday. Tuesday sessions are based on the synthesis of the key points from the 2020 series. If you go to our website and see the series for last year, you will notice that there were 30 invited speakers. So we carefully went through everything that the speakers said, and we synthesized the key take-home messages, and we have written them as a set of notes, which are also available on the course website. Some of the Tuesday sessions may have invited guests, but most of the material on Tuesdays is based on synthesis from last year's series. The Thursday invited sessions will feature invited guests from academia and industry. Each Thursday session will have two 30-minute presentations. Sometimes they may have 1 or 3 presenters, but mostly they'll have 2 presentations of 30 minutes each, followed by question and answering sessions. We will be recording the sessions, and the recordings will be made available on the website. For Stanford students who are taking the course for credit, they will be required to complete a quiz for all 10 of the Tuesday sessions and submit a written summary for any 8 of the 10 Thursday sessions. Given that this is a 1-unit course, this is a pretty light requirement. With that brief introduction, let us get into the topic of today. What is a knowledge graph? We will begin by first defining a knowledge graph, and then discuss why there is resurgence of interest in this topic. And to discuss that, we will consider 3 different applications: search engines, data integration, and artificial intelligence. In this process, I also want to convey to you what is new and different about knowledge graphs. We can define a knowledge graph as a directed labeled graph in which nodes and edges have well-defined meanings. A directed labeled graph is a well-understood mathematical concept, and we would teach it in our introductory discrete mathematics course. The main difference between what we teach there and what a course on knowledge graph should cover is the special attention that is given to defining the meanings of nodes and edges. We will be talking about different ways of defining meanings in this lecture, as well as throughout the series. There are many data models which use a directed labeled graph as the core mathematical representation. and they may refer to nodes and edges by different names. We will be covering the data models in next week's lecture, but for now, I just wanted to convey that in some data models, they refer to nodes and edges as subject, predicate, object triples. Okay, and in some other data models, they refer to it as entity relation, entity triples. Many of you may have seen class hierarchies, and in class hierarchies, the nodes are classes and the edges are labeled by subclass of or subset relationships. In each of these three examples, a directed labeled graph is the mathematical characterization of the underlying representation. The names associated with nodes and edges, they depend on the data model, their intended use, or the application context. Let's now take a concrete example instance of a directed label graph in which we are capturing a friendship relationship between Art and Bob. And this little knowledge graph here is saying Art is friends with Bob. Now, the first question that arises is how are we going to associate meanings with these nodes and edges? Regarding the nodes, we can say that Art and Bob, they represent people in the real world, right? Regarding the friends relationship, we can either describe the meaning of the friends relationship in English by simply describing it, or we could also say that we will associate the friends link between Art and Bob if, say, on a social network such as Facebook, Art has sent a friend request to Bob and Bob has accepted that request. If that has happened in the real world, we will put this friends link between Art and Bob. That's one way of defining meanings. So in the case of the subclass relationships, the nodes are abstract concepts. They're not individuals in the real world, but they are abstract concepts. In these cases, mostly the meaning is defined using text documentation. And if you're more sophisticated and you want to go further, you could specify or you would formalize those text definitions using some kind of a logical language, and you may have logical specification for the meaning of each of these nodes and how they are related to each other. The main point here is that there are many different ways to define meanings for nodes and edges. The meanings could be defined based on what has happened in the real world. They could be defined or captured in explanations written in a human understandable language. For example, there is a linguistic resource called WordNet in which the meanings of words are simply defined in English. The meaning could be defined using a set of axioms or rule as a logical specification. We can also define meaning using a set of examples. So let's say in our knowledge graph, we have a concept called cat, and we want to define its meaning. We could associate lots of cat images with that node. And we can say that the meaning of this concept cat is what is conveyed in these images. More recently, there has been a lot of interest in capturing the meaning using embeddings, which are calculated based on statistics on a corpus of text. We will be talking about embeddings later on in this lecture. But the main thing I want to convey here is that there are many different ways to capture meanings. And in fact, different ways to computationally capture meaning is the heart of the problem in many areas of computer science, including AI and database systems and many other related subdisciplines. Each of these methods that I have listed here are different ways of capturing meanings, and they serve certain purposes. They are useful in certain contexts, but these methods are not complete. They cannot completely capture the meaning, and all of them taken together cannot completely capture the meaning. And not surprisingly, there is a rich history of work in computer science in different approaches to capture the meaning, especially in knowledge representation and database systems. Specifically in knowledge representation, the earliest approaches used a notation called semantic networks, which is essentially a directed label graph. Semantic networks were evolved further into description logics, and there was also parallel development of a representation technique called conceptual graphs. On a parallel track in database systems, the early database systems, they had a network structure. They had a general graph structure, which eventually evolved into relational database systems, which are very popular today. But perhaps the most relevant work to knowledge graphs is the work on triple stores, where people are trying to investigate techniques when the data model is essentially a set of triples, right? So the point here is that this enterprise of capturing meaning or enterprise of storing information as triples, it has a rich history. There is, by itself, there is nothing new in it. And my hope is that my hope next is to explain what is new in this field. Why is there is a resurgence of interest? And I will do this by taking 3 examples. Search engines, data integration, and artificial intelligence. To explain the use of knowledge graphs in search engines, I will take an example which was introduced by Danny Vranicic. He used this example in his presentation last year, which was an opening presentation in the series. If you want to hear this example in his words, you can go to the website for last year and you can hear it directly from him. But for this year's course website, I've also linked a 2-pager written description of this example in Danny's words, which is actually quite interesting, and I encourage you to check it out. But what I'm going to present here is going to be my version of it. I heard Danny describe it, and I'm going to narrate this story to you in my words, and I'm calling it the Winter Tour example. So we go to our favorite, one of our favorite search engines, and we type Winter Tour Zurich. We get a set of results. The first result here happens to be a Wikipedia page, and then there is a set of images. We can click on the first result, which will take us to the actual Wikipedia page for Winter Tour. Now, what is interesting about the search results is that there is a certain area where they also show some facts. And it turns out that these facts are being pulled out from Wikipedia. Now, if you go into the Wikipedia page for Winter Tour, you'll be able to see that these facts are coming directly from what are known as info boxes in Wikipedia. So in this case, the search engine is now smart enough to realize that this data or structured information is available in Wikipedia, and this sort of information is of interest to people. It's able to extract that information, and it's able to show it right there as part of the search results. So in this way, the search results are being enhanced using the structured data available in Wikipedia. This example, however, is just the tip of the iceberg of what is actually possible using the structured data. And let's now actually look at the iceberg. Let's scroll down in the Wikipedia page for Winter Tour. And at the bottom of the page, there is a section where they mention twin towns, where they list 4 twin towns. 2 are in Switzerland, 1 is in Czech Republic, 1 is in Austria. Okay. Now, completely unrelated to Winter Tour, if you search in Wikipedia, there exists a town called Ontario, California. Okay. And if we scroll down on the page, down in the page of Ontario, California, we see this area here called Sister Cities. And in this area, they see an entry called Winter Tour. And that's why we are looking at the page of Ontario, California. Now, what's really going on here? If we understand the meanings of sister cities and twin cities, we kind of know that they are identical concepts. They are referring to the same thing. But the reference to winter tour in the Ontario page, it doesn't have a back pointer from the winter tour page itself, right? And there is no easy way to automatically resolve this difference. Ideally, we would like this reference to be symmetric. Now, that's a problem. That's a big problem. And one possible solution to this problem is Wikidata, which is a huge publicly curated knowledge graph. And let's look at how Wikidata solves this problem. In Wikidata, if we search for information on winter tour, we get a page like this. And if we scroll down, we will see that there's a relation name called Twin Administrative Body, where there's a reference to Ontario, right? And on the other hand, if you go to the Wikipedia page, Wikidata page for Ontario, there's a similar section, Twin Administrative Body, which points to winter tour. Now the relationship is systematic. Now what's really going on here? What's making this actually happen? Underneath, there is a directed label graph representation in which winter tour and Ontario are nodes, and there is a link, twin administrative body between the two. Okay. Now that by itself is not that interesting, but more interesting fact is that both winter tour and Ontario are connected to lots of other things. For example, winter tour is part of Zurich metropolitan area, which is in Switzerland. Ontario is in the United States, which is part of North America, etc. But the iceberg doesn't stop here. It turns out that there are many other people on the web, many other organizations on the web that are publishing data using Wikidata identifiers. And one of them happens to be Library of Congress. They put out a lot of information they have about winter tour on the web. And because they're using the same identifiers, it's very easy for us to link this information with the information which is available in Wikidata. Now, that by itself is also part of the story. It turns out that there are lots of other sources on the web which are doing the same thing. You know, they are linking into Wikidata, they are making links among themselves, etc. And this is a growing movement. Now, the real powerful thing about this structured data is that it's possible to run queries against it. So, for example, if we have a query such as display on a map the birth cities of people who died in winter tour, it's not that easy to run this query using information available in just one place. It requires us to query multiple data sources on the web. It requires us to understand their schemas. And one effort that is being made for understanding schemas is called schema.org. It's an effort to create a shared vocabulary that can be used for publishing data over the web. With the help of the shared vocabulary from schema.org, it's much easier to query the information from these sources on the web and to combine the information and present the results as part of searches on the web. This is not possible today, but the whole point of this example was that if we are able to leverage knowledge graphs, we will be able to improve the quality of questions or search results that appear on the web. Now you may ask, how real is this? How big is this? I don't have exact up-to-date data on Wikidata. This data is probably about a year old. A year ago, it had over 80 million objects, over 1 billion relationships, and it was linking to over 4,800 different public catalogs. I mentioned the Library of Congress catalog. That is just one of these 4,800 or so catalogs that Wikidata is currently linking to. So having presented this example, let me just step back and emphasize some of the unique features of this knowledge graph, and to also sort of pull out what's new about these knowledge graphs that are available today. First of all, it's a knowledge graph of unprecedented scale. People have worked on knowledge graph or directed label graph representations, but we've never had representations, directed label graph representations as big as they exist in Wikidata. Second, this graph was not created by a single person. It was created through a community effort. Wikidata has a community of curators who help create this data, and there are other organizations such as Library of Congress who are publishing data that is getting connected to Wikidata. The data which is in Wikidata, a lot of it is created by hand. It's literally people who are sitting down and typing it in. But there's a lot of data in Wikidata which is also automatically created. Maybe some of it is coming from parsing of Wikipedia, some of it is coming through some other extraction tools, maybe some of it is just through crowdsourcing. But there are multiple methods using which the data into Wikidata is being put in. And then there is explicit attention to meaning, right? Through schema.org, there is an explicit effort underway to make sure that the labels that are being used, they have well-defined meanings. Of course, I'm pretty sure there are some relations being used which don't have well-defined meanings, but there is a recognition that we have to be able to understand, agree, and specify the meaning of the relations that we are using so that we can do inference with them. And finally, the data in this knowledge graph has a clear, compelling use case, which in this case happens to be web search, which has billions and billions of users and billions of queries, which by itself is sufficient to justify its existence and further development. But there are other use cases for Wikidata. There are organizations out there which are using the information available in Wikidata for multiple purposes. Next, I will turn to the use of knowledge graphs in the data integration context. I'll start off by taking an example use case, which I'm calling a 360-degree view of a customer. There are many organizations out there who have hundreds and thousands of customers, many have millions of customers. And to manage those relationships effectively, they want to have a complete visibility, complete view of their customer. And the information about their customer, some of it is in their internal IT systems, but some of it exists out there. And these days, there are many data providers who are selling this information on a commercial basis, right? It's not in public domain, but it's maybe they are extracting this information from public domain, but because it's a value-added service, they sell it. So here's an example. PitchBook is a data provider service which curates information about who is funding who, like which VC is funding which particular startup, how much money they are funding, etc. FactSet is another data source which curates information about supply chain networks, like which vendor is supplying to which customer, and vice versa, right? Now, think about an application such as risk analysis, where you are making some lending decisions. It could be very useful for a company to know how the customers or suppliers of a particular company are doing and whether they might be in some trouble, right? And that kind of information could be very useful, but to make effective use of that information, they have to be able to correlate FactSet information with the information they have available internally. Similarly, for business intelligence purposes, if they want to go targeted marketing for startups who have recently raised huge rounds of funding, they would need information of the sort which is in the pitch book, but they have to be able to combine it with what they know about their customers internally. So solving this problem requires doing data integration. they have to be able to combine information coming from these different sources into one unified view. Now, data integration is a problem that has been around for a very long time. People have worked on it for decades. And the core challenge in solving the data integration problem is that we have to do translations of data across these multiple sources. We have to be able to figure out what elements of one schema map into what elements in a different schema. We have to be able to define those mappings. Or we have to have a shared schema into which all these sources are being mapped to, right? And these problems have been around for a long time. People have worked on it. There are lots of techniques that are out there. But why are knowledge graphs becoming popular or interesting for becoming data integration? One reason why they are becoming interesting is because they offer a schema-free approach to data integration. So what you do is you can take your relational data from multiple sources, you can convert it into triples, and you can store it in a graph database, and you have your first version of integration, right? Some people even call that simple translation as a knowledge graph, but strictly speaking, I mean, you haven't really solved the problem. You've just translated data from one format to the other. But the interesting thing is that in this case, the hard work of defining mappings, that is delayed until you actually need it, right? And this is more popularly advocated as pay-as-you-go basis data integration. As and when you have a particular business question, you go and look into your triple store and see what new connections you need to make. You go through the pain and cost of making those connections. And then once you made those connections, you have immediate value, right? So what a knowledge graph or schema-free approach to doing data integration has done is it has made the barrier to entry low. You can get started very quickly. Now, some people would say that, well, when you use a knowledge graph for data integration, it is easier to visualize the data. It is optimized for graph traversals. And, there is some merit in those arguments. And we have sessions later on in the series where we will be looking deeper into each of these aspects and seeing to what degree knowledge graph supports visualization, to what degree they are better suited for supporting graph traversals, right? But for now, it is important to just understand that knowledge graphs have become a popular approach for data integration because they reduce the barrier to entry. Let's now talk about how knowledge graphs are being used with artificial intelligence. And I'm going to break it down into use of knowledge graphs for output representation and use of knowledge graphs for input to machine learning. First, we will take the example of natural language processing. And let's take this simple sentence. Albert Einstein was a German-born theoretical physicist who developed the theory of relativity. Given a sentence like this, we can run the entity extraction task on this and identify entities such as Albert Einstein, theory of relativity, etc. Of course, entity extraction is more general than this in that in some cases it may extract numbers, it may extract dates, it may extract time intervals. But for most part, entity extraction, most common case of entity extraction is you're extracting noun phrases. Obviously, we not only want to do entity extraction, we also want to extract relations between the entities. So given a sentence like this, we can extract relations such as Albert Einstein was born in Germany, the occupation was theoretical physicist, and he developed a theory of relativity. Given those relations, it's natural to represent this extracted information as a knowledge graph. Now, we don't want to just construct this knowledge graph, we want to do inference with it. We want to associate meaning with what are the labels so that we can do question answering, we can do common sense reasoning, and derive conclusions such as Albert Einstein was a physicist, and Albert Einstein developed some new knowledge in physics, etc. I know that there are some people in NLP who say that, oh, we don't need to specify the meanings of these labels, but the real issue is you want to be able to do inference with them. So one way or the other, you have to characterize what these labels mean and what conclusions you can or cannot draw using a graph representation like this. Next, let's look at the computer vision problem. They're given a picture like this. We want to see what objects exist in this picture. And that is the standard task in object detection. And then next, we want to see how the objects are related to each other. So in this picture, we can see that a man is wearing glasses, the man is feeding a horse is eating from a bucket, etc. Right? And computer vision is getting better and better at identifying relationships like this. But just like in the NLP case, we are not interested in just representing this information in a graph like this. We want to be able to do inference or visual question answering using it. And for us to be able to do systematic visual question answering, we have to worry about the meanings of what are the meanings with each of these labels and what inferences we can or cannot draw using them. Let's now turn our attention to how knowledge graphs are being used for input to machine learning. Most current machine learning algorithms, they require numerical input. So for example, you're feeding certain data into a regression model or into a neural net, you need to give it a set of numbers. But if you're going to do entity extraction or relation extraction using any of these models, we have to give them numbers, but we have words, right? So we need to come up with some way of converting our symbolic words into numbers so that they can be fed into these learning models. So word embeddings and graph embeddings, they are popular techniques. They have become very popular for converting symbolic representations into numerical representations for input into machine learning models. And I will try to give you intuition into each of these. Originally, the word embeddings were developed to provide a tool to calculate word similarity. So for example, if we want to see like is similar to enjoy, we want some method using which we can automatically calculate this. But over a period of time, it has been found that these word embeddings are generally useful for a variety of language understanding tasks. And the key idea behind word embeddings is to capture the meaning of a word by counting how often it occurs next to other words. Okay, let's make it concrete, and let's say we have a corpus which has just these three sentences. I like knowledge graphs, I like databases, I enjoy running. Okay, from this corpus, I can calculate numbers like this. So for example, in the first row here, in the second column, the number is 2 because like appears next to I twice, right? And for enjoy, the number is 1 because enjoy appears next to I only once, right? And I can similarly calculate numbers for the other positions and create a matrix of the form that you are seeing here. Given a matrix like this, we usually refer to it as co-occurrence counts. And we say that a meaning of a word is captured by the vector that corresponds to each row of co-occurrence counts, right? So in this case, the meaning of I is captured using this first row of numbers. And if you want to calculate similarity between two words, we simply compute the distance between the two vectors. So in this case, we would, if you wanted to see if like and enjoy are similar to each other, we would see, what's the distance between the two. Now, the key insight here is that we have taken our words, which are symbols, and we have turned them into numbers. And now we have the numbers which we can feed into our learning algorithms. The reality, of course, is much more complex than the story I've just given you, because our text corpus is not going to have just 3 sentences. It's going to have billion plus words. And if you use the naive approach that I just explained, the storage requirement will blow up. And in practice, you have to do dimensionality reduction. Typical word vector representations, which are being used these days, their size is typically in the range of 200. And there are other techniques like linear algebra, like singular value decomposition, and techniques for automatically learning how to pick those 200 numbers using which we are going to represent a word. There's a whole course on that, right? If you take the NLP course, that is primarily devoted to how to do different forms of word embeddings really well. You see the word embeddings used in practice a lot. So for example, if you go into search engine and you start typing, it starts predicting what are likely next things you might type. And it's essentially using a language model which is driven by the kind of word embeddings that I just explained. Next, let's now turn our attention to graph embeddings. A popular application area for graph embeddings is recommendation. So if you're on an e-commerce site, these companies are very interested in recommending to their customer what other things they should buy, right? And they have a lot of historical data on what similar customers have bought in the past. And this data exists in graph form. And in this graph, each node is a product, and there's an edge between two products if those products tend to be bought either after each other or they tend to be bought together, right? But essentially, this is a symbolic structure, right? And machine learning is very good at predicting things, but you have to give it numerical input. But if you want to feed this historical trend, which exists in the symbolic form, and we want to use machine learning to do the prediction, we have to convert it into some numerical form. So the problem and the goal here is very similar to what we had for the NLP case. We have to be able to take this discrete symbolic structure and we have to convert it into vectors so that we can calculate node similarity, we can calculate a difference between nodes, and we can send them as input into the machine learning algorithm. Now, to understand this, I'm going to give an analogy. And since we have understood how we calculate word embeddings, we can say that, well, the sentence that we worked with can be viewed as a linear graph in which each node is a word and there is an edge between each successive pair of words, right? And the word embedding calculation that I showed you could be viewed as a graph embedding over this linear graph, okay? So this analogy is really helpful because it helps us immediately see how we would take a discrete graph and we would turn it into a linear path. All we have to do is we have to randomly walk the graph, right? And every time we randomly walk the graph, we will get a linear path. And then on the linear path, we can count how often which nodes co-occur with each other, and we can develop a matrix of co-occurrence counts, just like we did it for our sentence corpus, okay? Now, given this approach, we can calculate graph embeddings, and actually the embeddings for the nodes, they are referred to as node embeddings. And given these node embeddings, we can easily calculate node similarity and how close they are to each other. As I mentioned, the word graph embedding is usually referred to the embedding for the whole graph. If you want to calculate the embedding for the whole graph, one trivial approach would be to simply take the sum of the individual node embeddings, and it gives you the embeddings for the whole graph. Now, I should say that what I presented to you is a naive and simplistic picture because I'm trying to convey here the intuition, and I'm trying to explain, how these knowledge graphs are related to machine learning, and why and how they are being used. And just like word embeddings, there is a whole separate course on how you calculate these graph embeddings and how you do effective inference using them. But I hope with the explanation I've given you, you have the basic intuition of how these embeddings are being calculated and what purpose they are serving. So to summarize, the relationship between knowledge graphs and AI, the knowledge graphs are being used as output representation for both natural language processing and computer vision. And they are also being used as input to machine learning wherever we have any domain knowledge or background knowledge which is available as a knowledge graph. The the embedding approaches make it possible for us to input that knowledge into these numerical models so that machine learning can make better predictions. With that, I will like to summarize today's topic of what is a knowledge graph. I have argued that graphs are a fundamental construct in discrete mathematics, and the main value that knowledge graphs add over graphs is defining the meaning. That is really the crux of the problem for knowledge graphs. And we want to define the meaning in a way that our programs can understand with them, and they can work with the meaning in a principled manner. Obviously, there has been a lot of work on this problem over the years, over decades, and there's a rich history of work on this topic, both in knowledge representation and databases and many other areas of computer science, including NLP. The recent surge in interest in knowledge graphs has been driven primarily by the use case of web search, because in the web search, we want to be able to make the results better. The search has billions and billions of users, and this data seems to help in improving the search. So there is certainly increasing interest in making use of knowledge graphs in that context. There has been a lot of progress in NLP and vision. Up to many years ago, people were struggling just to identify objects in an image. There was no need to build a knowledge graph out of it. But given that there has been a lot of recent progress, the edge detection, relation extraction, all of those technologies are improving. So there is need to better organize this knowledge, and knowledge graphs seem like a great starting point for that purpose. And similarly, machine learning has also gotten better because of the well-known reasons of compute power, improvements in compute power, improvement in availability of data. And within these machine learning models, we want to be able to make use of domain knowledge, right? And if the domain knowledge is structured as a graph, there are now techniques available using which the domain knowledge can be input to the machine learning. So to conclude, the final point, what's new? What's new in all this? And I want to summarize that in basically three main points: scale, bottom of development, and multiple modes of construction. By scale, I mean that even though directed label graphs have been used for a long time, but the scale at which they are being constructed now, for example, as in Wikidata or in many NLP vision tasks, that's new. I mean, we've not had knowledge graph representation or directed graph representation used at that level of scale. Second is bottom of development. The classical work in knowledge representation and databases has been driven by a top-down design. You are building a new application, you sit down and you carefully think through your domain model, you define your classes and relations, and then you build a piece of software. So it was driven by a top-down approach. But what we are seeing in the recent past is this bottom-up development, where the knowledge graph development happens based on what data is available, what data somebody has put out there, what data you can buy in the market, what we can extract, what we can actually learn, right? So all of those things are driving this bottom-up approach of creating these knowledge graph artifacts which I think is new, right? It doesn't mean that top-down design is not important. I think top-down design still would be required at some point because, as I said, the crux of the problem is meaning, right? Even if you gather information in a bottom-up manner, you still have to be able to reason with it. So you have to put some boundaries of meaning around what you have extracted in a bottom-up manner. Finally, now we have multiple modes of construction. The classical work in knowledge representation that was primarily driven by uh, manual knowledge engineering, right? That manual approach to knowledge engineering is still happening. A lot of the knowledge graph creation work is done manually. Somebody's typing it in. But we are also seeing greater use of automated extraction methods like NLP and vision methods. We are also seeing a lot of crowdsourcing approaches. All of these approaches are coming together in the creation of these large knowledge graph artifacts. Some people might say that it's all automated, but I don't think that is quite true. I mean, any knowledge graph construction which is of any significant quality, there is definitely some manual effort going into it, even if it is at the level of doing data labeling or data validation or whatever. But the manual effort is still part of the component. But the main point here is that we are now able to mix these methods in creating these large, complex knowledge graphs, which was not really possible until, say, a decade ago. With that, I'd like to conclude my presentation and give you a preview to our session for this Thursday, which will build on this theme of what are knowledge graphs and why we need them. Our speaker would be Professor Chaitanya Baru from National Science Foundation, where he would give an overview of this topic area and also tell us about some interesting projects that they are currently funding. With that, let's close today's session, and I will look forward to seeing you on Thursday. Thank you.